Volumes of cross sections. Let's begin. So, a little backstory and how do you find volume? And I like to think about it like this. So, when you integrate a line, so a line of a function, you get the area. And I think that's one dimension going to two dimensions. So, when you integrate an area, which is a second dimension, you're going to get a volume. So, you're in 3D. And the general formula to calculate this is right here. So, volume is the integral from a to b of a of x dx, where a is your area function, whatever that function may be. So sometimes the challenge is how do we figure out that function? Generally, when we're doing cross section shapes, they are going to be cross sections using shapes that we know. So maybe a square, a rectangle, a semicircle, a triangle. That's what I think Khan Academy does. I think the AP test only covers that. So equilateral triangles in there. I mean, could figure out that formula from a triangle, but there it is in case you needed to. I don't know if you need to. So the key to solving these kind of problems, you know what? What does a cross section look like? Let's just show you this. So the idea with the cross sections, we have our area shape would be two-dimensional. We're going to say like, oh, the cross section is going to be a bunch of squares that are perpendicular to the x-axis or whatever, perpendicular to the shape, the function. So if this was a bunch of square cross sections on this triangle shape, it'd look like this. This would be semicircles on this function that looks like it was like about the square root of x, similar to that. And then you got this like, I don't know, it's like parabola shape going on with these triangles. So this kind of gives you a representation of what these shapes may look like right here. So you're growing these shapes now. It's little cutouts. In general, it'll be like a smooth curve, but this gives you the idea of the kind of shape that will be created. I think the challenge of this is sometimes visualizing this can be very hard. So what do you have to do this formula? Well, you got to figure out your limits a and b. Sometimes that's given. Sometimes you need to see where things intersect on the functions and on the graph. And you want to know what the shape the cross sections are. It will be mentioned in the problem somewhere. Squares, rectangles, triangles, semicircles. Like it. And then use that formula. Now, the trick here is sometimes the variables in that formula might be constant or might be one of the functions. So, for example, you get area. Say if I did this rectangle's base times height, they might say, oh, the height is this function, whatever f of x, but the base will be like 3 times that function. So it'd be 3 times f of x. Or maybe the base will be just 2 itself. Typically, these variables are going to be that one of the functions involved. And you'll see it. I think you just got to do some examples. You get the idea. So let's take something like this. Base of a solid of a region. I have this one right here. And the cross sections perpendicular to the x-axis are squares. So if you were drawing this, and I'm going to do a bad job drawing, you have like a square jumping out like this, and then squares jumping out. I'm not really good at drawing this stuff. Really, really bad at that. But the idea is you have this square shape kind of bumping out, whatever. It's getting bigger. So I know I have squares, and I know this function and y-axis, it's right here. What do I have to do? I don't know. I have these questions in here. Oh, I remember. So what's the area of this function? Well, let's see. Okay, ignore this. Well, we know we're doing squares. What if these were squares as cross sections right here? I'm going to do this one first. So the area is going to be side squared because we're dealing with square cross sections. And so it's one length of one base. Well, the base is going to be the length from x-axis up to that function right there. And that's going to be the y value of that function. So the base is just going to be negative x squared plus 4. So I know my area formula is going to be negative x squared plus 4 squared. So as an integral, as a volume, I can say my volume is the integral from, and this is negative 2 to 2, of negative x squared plus 4 squared. So that would be my function. I can plug it into a calculator or do whatever. I'm going to avoid that. Now I'm going to take that same one. I'm going to ask this question. What if the cross sections are rectangles instead? Then with the height is 3 times the base. Okay, so it's 3 times the base. So you can have like really tall rectangles coming up. Whatever. But it's the height is 3 times the base. So let's draw a picture. Remember, area is base times height. area. And so I'm going to draw that picture over here. And the length of that base is going to be negative x squared plus 4, right? Because just like in the squares. But this side is going to be 3 times. It says 3 times that base. So 3 times negative x squared plus 4 would be this side. My total area is base times height. So setting up that rectangle, the volume is going to be still from negative 2 to 2 of 3 times negative x squared plus 4 times another negative x squared plus 4, where this base, this could be like the base or the height or whatever, and one of these is the height. So if you're kind of, I got that in reverse, but you get the idea, right? So you plug those into a calculator and you'd be done. Now let's ask, what if the cross sections are semicircles, right? So same shape, if we did these as semicircles. So you have these half circles coming out like this, kind of like this shape coming out. Oh, wow. That is a really bad drawing. I can't do it to scale. So semicircles look like this shape. Now, this is where it's a little trickier because the area of a semicircle is 1/2 times pi times r squared. Now, r is this radius. Now, the radius isn't the entire length here of that function. The radius is half that function. The whole thing is diameter. So your radius is just this part. So my formula here is going to be 1/2 times pi times half of this distance. So negative x squared plus 4 over 2 squared. Half of that. So I can set my volume equation as the integral from negative 2 to 2 of, I'm just going to say pi over 2 times r squared. So negative x squared plus 4 over 2 squared dx. Yeah, I could simplify things. It was like, squaring the top, squaring the bottom is going to be a 4. You wanted to rewrite that. It's pi over 8 because it'll be 2 times 4 times negative x squared plus 4 squared from negative 2 to positive 2. Don't have to, but that's how that works. That's like the difference. Same function here, but depending on the shape, you change what you're writing. Let's try something else. Like, what if it's not obvious where those limits are, right? So I have a base of a region enclosed by y equals 1 and x squared over 9. Let's assume I don't have a calculator. If you can visualize these graphs, it really would help you out. But let's say cross sections perpendicular to the x-axis. So maybe I'm starting to draw this out. If I had the axis, I know y equals 1. Let's pretend that's y equals 1. Could be this line here. And then x squared plus 9. Well, I think it's helpful if you knew what x squared plus 9 looks like. This is going to be a parabola shape. It's going to be divided by 9. I think that's going to make it a wider parabola. Since it's divided by 9, it's going to make it wider. Okay, so that's what it looks like. But what are these endpoints? Where are those endpoints? And ignore. Why do I have these? Let's just pretend they are. Oh, we'll follow these rules. Okay, let's actually go backwards. What if the cross sections are squares? I'll do all 3 of these. Why not? So I got to figure out what these endpoints are right here and here. So what I'm going to actually do is I'm going to set these equal to each other. So I'm going to go y. So 1 is equal to x squared over 9. Let's solve for x. Multiply by 9 on both sides. And so x, we square root both sides. X equals plus or minus 3. 3 and negative 3. So that's negative 3. And that is going to be positive 3. All right, set them equal to each other. It'll tell you the end where they intersect. Okay, so what if the cross sections are squares? And that would be, I have to do the square shape coming up. The length of this square here would be, and draw a square. The length of this square is going to be the length between these two functions. So it's going to be the top minus the bottom. The top one in this case is the line. So it'll be 1 minus x squared over 9. So that squared is going to be our function. Our volume function would be from negative 3 to positive 3 of 1 minus x squared over 9 squared. And that's how you do squares. Now, what if we had rectangles with the height that is half the base? All right. I'm not going to say half the base. With with the height, I want to say this differently. With the height of 2. Maybe the height's 2. It's just a constant number. All right. So you're thinking of like rectangles that are like bumping up a little bit, and they're always going to have the same height. It's not based off of what the length of that base is. So I'm gonna see pretty wide rectangles and assume this height's going to be 2. The length of the base is going to be the difference between those as well, just like the square. So my volume here is going to be -3 to 3 of base times height. So 2 times 1 minus x squared over 9 dx. And that'd be it. All right, so let's say equilateral triangles. And you go, oh, what was the equilateral triangle formula? And no one remembers that. Square root of 3 over 4 s squared. Cool. So you have equilateral triangles. Now sometimes when they say these, sometimes they say equilateral triangles, but one leg is on the bottom. So they're equilateral triangles where I'm going to say the hypotenuse is on the bottom. I guess you know what I mean, right? We can use that formula. Sometimes they're like one of the legs is on the side, so you would do it differently. It'd be like sticking up, like as a right triangle. Oh, equilateral triangles would be different. 60 degrees. What was I thinking? Thinking right triangles. I'm thinking isosceles. Anyways, right triangles. Area formula is going to be square root of 3 over 4 side squared. So volume is going to be -3 to 3 still of square root of 3 over 4 times 1 minus x squared over 9 squared. That's it. All right. That gives you different ideas of what those could look like. Any other problems? I mean, these are all basically exactly what I just did right up here. Could try some others. I don't think I need to do more. I think that gives you the idea. Just understand when you have to plug those in. And yeah, that's it.